Alright, so that was just a 10-minute introduction. So these recorded lectures, it would take me 2 hours to cover each of these lectures, so we're going to go through them a lot quicker than that when we record. Just because, notice here it says AMC 2015 Summer School course, but we can change, I can edit that myself. Okay, so the method of characteristics for linear equations is what we're going to start with. So we're actually going to start with a fairly gentle introduction. Some of you may have already seen this. It depends on the course that went before. So we're going to start gently. We are going to do something a bit nasty though, because we're going to draw the picture of these, okay? So you might, I'm sure you wouldn't have done that. You'd have just written down the solution and been happy with it. But we're going to write, we're going to draw some pictures of it. So you may or may not have covered this, but it's just a warm-up exercise really to get us going and to get us into the same page before we start into the nonlinear PDEs. And sometimes these other nonlinear PDEs, these introductory ones like the traffic waves, will have also been covered before, but we'll just go through them again. Okay, so for some, just to get us all onto the same page basically. Okay. So just to be clear here, I'm just going to go through and explain to you how to solve this. Just going to go through these notes here. That's what's written down here. Okay, example 2, and we'll finish up here. Okay, and then then that will be the end of this first lecture. And then you've got this idea in the assignment goes with this. You've got to try and draw some of these pictures, and of course you can use the code here to draw it. And we'll maybe look at this picture here so we can see what they're all about. Okay, we'll explain what's going on. Okay, so what have we got here? There we go. The other one's ready to dismiss. The other one that I just recorded is ready. All right, so let's have a look here at the method of characteristics. So this is for linear equations, okay? And we're going to do it for nonlinear equations for the lectures 2 through to 4. So let's start out with this equation. Now let's just go here now. Du dt plus du dx. There's lots of notation for partial derivatives, and I've got my own one as well. I'm going to write this as dt u plus dx u. Okay, this is the best notation there is. I just feel like certain of it, it's actually used by people. If you want to seem fancy, I use it in my papers and all of that stuff, because the derivative is an operator that acts on the function and maps it to another function by differentiation. So this notation here is not super helpful, I don't think. Okay, occasionally you get some benefit by it, but I don't. Makes it completely clear that it's an operator acting on u. Okay, and we've got x goes between minus infinity and infinity, and t is greater than 0. It starts from some initial state. So we've got u at t equals 0. You know the answer to this problem, okay? I'm just going to try and find it for you. So what we do is we go out here, and here's the t plane, and here's the x plane, and we imagine some curve here, right, where x is equal to big X of t. It's very difficult with notation and maths to distinguish between the point and the function. So the big X represents the function, x represents the point. You could just have small x. I'm not sure how helpful that is. So that's a curve, a parameterized curve. It might cross on itself. X of t. Oops. It's x comma t. It's the set of points which are equal to x of t comma t. All right. So what we've got here, we've got u of a function of x and t. It's just a function of x, isn't it? Now along this curve, we're asking what is the value of u on this curve. It's u is equal to u of big X of t and comma t. And then we say what is the derivative of this with respect to t, and it's the full derivative. So how does x change? How does this function u change along this curve? And it changes by, now then this thing here is the partial derivative of u with respect to x. So it's dx dt by the chain rule times d sub x of u plus d sub t of u. That's the total change along this curve. Now, we know that the partial derivative of u with respect to x is minus the partial derivative of u with respect to t. So we can write this as dxu times dx dt minus 1. So that's the total derivative. So, I haven't really done anything here at all. If dx dt equals 1, then the u d by dt of this function u of x of t, comma t must equal 0. So u is a constant on the line. Okay? So dx dt is equal to 1 means big X is Z. Right? So which is x equals x of t, right? So it's big X here, right? Function, which is t. So we wouldn't normally, we'd quickly move out of function into point mode. So I'm not sure whether writing the big X is helpful or not, but it's t plus a constant c, right? So what that tells us is that u of t plus c, comma t, is a constant, right? So as long as we're on that curve there, it's a constant. And if we set t equals 0, I'm running out of space here. I'd rather just keep squeezing it in. Let's try and risk that. If we set t equals 0, we get u of c, comma 0 is equal to f of c. So we're all good to go. The only problem is we've got to solve for c. It's the final stage of this process. I'll go for another colour purple. So now we solve for c. Now c is equal to x minus t. So we get u of t plus c, which is x, comma t, equals f of c, which equals f of x minus t. And that is the solution to that equation, right? And that you could have done that from the start if you remember how these things work, right? The derivative with respect to t will be minus the derivative with respect to sigma. But we pulled out the solution here for that function, and we calculated the characteristics for this very simple example. So the way I'm sort of doing the general case first, I've done a simple example for us first, then I'm going to do the general case.